The search of extraterrestrial life. It has been the driving force behind much of space exploration, sending both robots and humans into space in hopes of finding hints of life. While much of that has historically been focused on the Moon and Mars, the attention is shifting towards other targets. One of these is the Jovian moon Europa. Entirely covered in ice and snow, and with an average surface temperature between -200 and -150 degrees Celsius, it might seem like an unlikely place to search for life, especially as it lies within Jupiter's radiation belt, exposing the surface to radiation levels high enough to kill a human within less than an hour. However, far beneath that harsh icy crust, there might exist a vast subsurface ocean. Shielded from the radiation and heated by tidal forces and geothermal vents, it may be one of the best spots in the solar system for life to have developed away from Earth. But an endeavor to find and study this environment would be one of the most challenging missions in the foreseeable future, according to Alex Ellery, whose book Planetary Rovers, Robotic Exploration of the Solar System this video is strongly based on. The first challenge is simply the distance to Jupiter and Europa. As a lot of delta V is needed to transfer from Earth to Jupiter, only a relatively small payload of a few tons is possible with current rockets. Additionally, power is particularly troublesome. Solar power is severely hampered, as it only produces about 4% as much power as in Earth orbit. On the flip side, there's a major power demand for heating and communication. For this, large antennas are needed to reach sufficient directionality and gain to traverse the distance with reasonable signal power. These issues apply to any probe to the outer solar system, though due to the proximity to the icy surface, a Europa lander would need even more heating, and solar power would be even worse due to the prolonged nights. As the surface is still scientifically interesting and contamination of other mission components should be avoided, a sky crane-like landing system would be most advantageous. This would reduce contamination, avoid pitting off the surface, and throw up less debris. Additionally, it would make space on the underside of the lander for more instruments and easier deployment of other systems. The harsh radiation would not keep the mission's electronics untouched either, as it would exceed the typical radiation rating within less than a year. While other mission components will be shielded by the ice, the surface segment would need to have radiation vaults enclosing its electronics to protect them. This leaves us only with a surface lander though, while our interests lie deep beneath the surface. Estimates vary, but most think the ice crust ranges from a kilometer in the thinnest spots to tens of kilometers in most areas. To reach the ocean underneath, we need to be able to make our way through the icy barrier. This could be achieved either through a separate tunneling apparatus, creating a tunnel for the ultimate payload to pass through, or through a self-contained assembly that also carries the scientific payload. Such a device could be described as a cryobot. The most obvious method may be to simply drill a shaft down, breaking up the ice and moving it out of the way, like one would do with dirt and rock on Earth. However, on Earth you usually use a drill head with following pipe segments to fill and stabilize the created cavity. As this would necessitate a lot of mass for just the drilling mechanism, it is not realistic with our very limited mass budget. Not doing this would pose a significant risk of the borehole collapsing, jeopardizing the entire mission. This would similarly apply to a drill-based cryobot, as it would have no way to properly stabilize the borehole above itself. A better approach unique to this kind of environment is melting through the ice. By heating the tip of the probe, melting and sinking into the ice below, and then letting it freeze again above, there is no risk of collapse or inherent abrasion. To make this faster and more efficient, a high-pressure jet of heated water can even be used, traveling into and breaking up the ice ahead, creating a sludge instead of fully liquid water. Subsequently, this would get pumped through or around the robot, collecting above as it slowly cools. The sides of the bot would also have to be slightly heated, to avoid premature refreezing, ensuring a buffer of liquid. The drilling speed could be controlled either by controlling the thermal power transferred into the tip, or adjusting the buoyancy within the water envelope, affecting the downwards force against the remaining ice. Realizing this still is not easy though, as heating and melting through kilometers of ice within a reasonable time frame of a few months requires a significant amount of power in the order of kilowatts. With solar power out of the question, the prime option remaining is nuclear power. Radioisotopic thermoelectric generators, as they were utilized on other missions to the outer solar system such as Cassini, Voyager and New Horizon, or the similar radioisotopic heating units, would struggle to provide sufficient power, leaving a miniature reactor as the best option. Small reactors have already been utilized and proven in space, in programs such as RORSAT and SNAP. A more modern design could be used to provide sufficient thermal power within a reasonable mass. But this is only the start of the challenges facing the cryobot. While we know relatively little about the composition of the ice layer, it is likely it contains fault lines, caves, rocks, and other hazards. Hitting any of these would likely jeopardize the mission, necessitating a system to avoid these. This involves both detection and steering. Detection could be achieved through sonar, especially adapted and optimized to detect not just solid rocks, but also gaps and irregularities in the ice. Once an obstacle is detected and localized, an avoidance maneuver can be calculated. A very limiting factor here is that we cannot go back up, only allowing avoidance through steering to the sides. Differential heating of different parts of the tip, or mechanical angling of the bot within the cavity, can allow steering of over 30 degrees to the side. As our movement is either largely or completely powered by gravity, more aggressive angles become quite difficult. Due to this, avoidance of a large obstacle must start early to move around it, in turn necessitating long-range detection, multiple kilometers ahead. Despite these efforts, overly large obstacles may still be detrimental to the mission. To mitigate this, the tunneling site should be carefully chosen. To aid in the selection, the ice layer in general should also be studied more closely, potentially by a prior surface lander or rover mission. This could also identify the thinnest spots, minimizing the distance the cryobot needs to traverse. One of the most prominent features of Europa, the long fault lines and surface cracks, hint at another issue for the tunneling operation. While most drilling probes and remote underwater vehicles on Earth are tethered and maintain connection through that tether, doing the same on the cryobot would not only be heavy, but also likely not work. The fault lines and cracks are formed as the ice shifts, from tidal forces and plate tectonics, exerting forces far too great for a tether caught between two of them to sustain. Wired communication or power transmission thus are likely not feasible. As such, an alternative communication system must be conceived. A possible alternative would be independent relay points. These could be powered by small RTGs and be just a few centimeters across. They would be released from the cryobot periodically, deploying small antennas and embedding themselves into the ice as it refreezes behind the cryobot. Any radio signal they receive, they would re-emit at a higher power, passing it on from relay to relay, establishing a link between lander and cryobot. With this configuration, such a cryobot could feasibly reach the underside of the ice layer, anchoring itself in the ice just as it reaches the water, getting ready to deploy the actual scientific payload, the Hydrobot. To cover a large area and gather as much scientific data as possible, an autonomous submersible should be utilized. This way the instruments can take measurements in many different areas, from the ice-water interface, preferably all the way down to the sea floor. There it can analyze the soil for organic material and remains of ocean life forms. Also it could explore the ground for interesting formations and areas, such as possible geothermal vents. These are believed to be a prime breeding bed for early forms of life, as they provide heat and numerous reactive or otherwise sparse chemicals, such as sulfates, metal salts, and ammonia. With organisms readily multiplying in such an advantageous environment, it would be unlikely to miss life forms if they exist, as they would likely exist in large numbers concentrated around the vents. To achieve this, it must combine an autonomous submersible with a deep diving research submarine, as the seafloor may lie over 100 kilometers below the ice layer still, exposing a submarine to thousands of bars of pressure, far exceeding anything vessels on Earth are exposed to. This necessitates the most pressure-tolerant of designs if the ground is to be explored. This can be achieved twofold. Firstly, to resist the pressure, spherical chambers should be used, made out of titanium, aluminium, or composites to minimize mass. These need to also be corrosion resistant, as salt water at these pressures is considerably corrosive. To improve the hydrodynamics, a flooded outer hull can be utilized to encase these spherical chambers. Secondly, by filling these chambers with an inert liquid, such as oil, the insides can also get exposed to the heightened pressures, reducing the pressure differential, and thus the stresses. This would be ideal for electronics that cannot be exposed to water but can withstand the pressure by being submerged in oil instead. As there aren't any inherently non-pressure stable payloads, such as humans, this combination would be ideal to allow a dive all the way to the seafloor. While with that design our Hydrobot can withstand the pressure, other questions remain, such as of power and communication. Power would similarly be achieved through a miniature reactor, though an RTG may be sufficient for this application, which would require a lower mass and complexity. Communication would get more and more difficult the further the submersible leaves from the cryobot. For short-range exploration, a tether would be possible, though it would quickly become too heavy when wanting to reach scientifically more interesting spots. Acoustic communication would reach a bit further with lower weight, achieving up to 10 km range with a reasonable data rate. At further ranges, the slow round-trip time would become an issue, potentially limiting the data rate severely in combination with increased errors. For even longer range, current-day submarines utilize extremely low-frequency radio waves, as higher frequencies get attenuated too strongly by the conductive saltwater. These low frequencies only allow for around 10 characters per minute, useful for little more than basic commands and health. A more modern option may be optical laser communication, though the viability of this would highly depend on the turbidity of the water, potentially making it impossible. High data rates could however be achieved through direct docking, either to a short tether or the anchored cryobot directly. A feasible operation mechanism would be for the Hydrobot to completely autonomously explore and gather scientific data before returning back to the cryobot for data transfer. This, however, would require a high degree of autonomy and reliability not yet achieved on interplanetary craft. In turn, other options would severely limit the goals of such a mission, confining the Hydrobot within around 10 km of the cryobot, far away from the lower portions of the ocean and the seabed. However, it would still be unlikely that the Hydrobot could reliably identify all scientifically interesting targets. To improve on this, the exploration data gathered in the previous expedition could be uplinked to Earth, where scientists select areas of interest for the next exploration to visit and conduct experiments at. This would require accurate and reliable navigation to be able to return to previously visited sites. Navigation provides another major challenge for such a system. While finding landmarks against the ice layer may be possible, once in the vast expanse of the open water, no landmarks will be usable. Localization has to purely rely on the cryobot, or possibly receive no corrections at all during the descent to the seabed. This may introduce significant drift due to strong and unpredictable currents, potentially making a return to the cryobot unreliable. Deploying positional beacons against the ice surface a certain distance away from the cryobot may help with localization by providing a longer baseline, though a strong attenuation through many kilometers of water stays a problem. Sonic time-of-flight methods may work, though are prone to error from variations in temperature and salinity. This is still an open issue also found in Earth-based autonomous submersibles. Lastly, there remains the topic of the actual propulsion and movement of the Hydrobot. Various methods have been developed on Earth for a wide range of applications, from energy-efficient gliders to highly maneuverable thrust pod-based craft. While a glider design might prove useful for surveying large areas, as it is relatively fast with minimal mass used for power and propulsion, it would likely be unsuited for precise and prolonged inspection of a single spot, such as to take samples or observe a geothermal vent. The most widespread design on current AUVs of an elongated craft and propeller with control surfaces similar to a torpedo reduces drag while enabling a high speed through active propulsion. Energy on a craft powered by RTG or reactor, such as the proposed Hydrobot, is largely just constrained by total time and a maximum sustained power, not by a limited amount of fuel. This makes efficiency less detrimental, as power is always available regardless of whether it is utilized. A design such as this would allow for fast travel, though similarly struggle with precise movement and orientation, as steering is only possible while moving. However, incorporating orientation thrusters into the body of the craft alongside reaction wheels would enable the execution of these scientifically relevant tasks. This could combine comparably high speed with maneuverability and precision. Designs like these already exist and are well proven and tested. The total mass budget may still be very restraining, though this could only be determined by a more thorough design evaluation. Larger rockets or separate launches of the subsystems could also ease this restraint, likely making the mission feasible with sufficient funding. But this kind of system would not be limited to Europa. Plenty other environments within our solar system could be explored with an adapted variant. Enceladus, a moon of Saturn, is very similar to Europa in many aspects and is also believed to harbor a subsurface ocean. Due to the slightly further distance, a bit more delta V would be needed, but the system itself would have to only be minimally adjusted. Staying around Saturn, Titan is known to have giant lakes of hydrocarbons on the surface, an environment unmatched on Earth. For this, obviously, no cryobot would be needed, and it might be advantageous to modify the lander to float and land directly on the lakes, instead of finding a method to let the hydrobots into the lake from the shore. The other way around, the cryobot without hydrobot could be utilized on Mars, drilling into its polar ice caps, searching for clues as to the climate history, similar to ice cores from the Antarctic. On that note, it would be similarly applicable to subsurface lakes discovered in the Antarctic. This would be both useful to gather scientific data and to test the system in a comparable but more accessible environment, allowing for prototyping. This is already being done on glaciers, as tunneling cryobots are already being developed. Concepts like these may be the next Mars rovers, bringing us closer to understanding the origins of life, and potentially finding other life within our solar system.